Thanks. Good morning, everybody. I'll be talking to you about our distributed database service at Cloudant. I'm going to kind of do a survey of some pieces of the stack that, where we encountered some technical challenges, where we felt design decisions were important. I'll kind of split it up into three parts: the database, the distributed aspect, and the service aspect. So the database is based on a project called Apache CouchDB. I'm one of the developers of this database. It's a JSON document database. It's not a relational database. I think that it's known for being robust, having good support for concurrent client access, and being fault tolerant. You put JSON in, and you can pick that out by primary key. If you want to generate indexes on the database, you can do so. These are called views, and they are built using JavaScript MapReduce functions. So instead of a create index command in your relational database, since this is JSON and you can't quite so easily pick out individual pieces of it, you might have arrays in there or nested objects or all sorts of things, you write a JavaScript function that takes these documents and decides what piece of them goes into the index, if anything. And one of the really neat features of CouchDB is its support for multi-master incremental replication. And we'll talk about how that plays into our service in a little bit. But it's baked deep down into the core that you can replicate with any other CouchDB server. Even if you've never seen it before, even if you haven't seen it in a long time and the two of you diverged, you can issue these replications, and the database will kind of put things back together. And at Cloudant, we offer, as I said, a database as a service. And in the course of building that service, we developed and open-sourced a high-availability clustering layer for CouchDB that we call Big Couch. The principles behind that clustering layer are similar to some of the other ones that you see in distributed NoSQL databases, like Bash's React, for instance. Consistent hashing is used to route the documents to the different partitions of the database. It's got this quorum functionality to decide when to reply to clients on reads and writes. In all, I think we find it's a nice fit for Couch's core features, and provides us with the ability to scale our service for large numbers of users with large databases, and to be able to survive kind of some of the failure modes that occur when hosting in various data centers. So that's the overview of CouchDB and Cloudant. First topic I want to talk about is log-structured storage. So in the bad old days, you had systems like X2 or MongoDB 1.0 that would just write things in place and kind of hope for the best. And if you had some sort of power failure, somebody pulled the plug, there was a kernel panic, you had to go do an FSIC, or you had to go and repair the entire database to kind of put things back together and figure out how much you actually wrote successfully, and where you might have to deal with some corruption. So that kind of sucks. People got smart and realized that, well, if we write to a log file what we're going to do before we do it, and we make sure that that log file is durably committed, then if something bad happens, we can figure out, OK, we got to replay the log and re-execute those last few steps that didn't get through. This was journaling in ext3, right? Or the write-ahead log in any number of databases. InnoDB, the storage engine for MySQL, has a log where the transactions are written before they're actually applied to the main storage. But the main storage is still an update in place kind of thing. If you take it a step further, you think, well, maybe I shouldn't do update in place at all. Maybe I should leave the stuff that's written and write something else new in a different place, and update data structures to point to that new stuff. And that's copy on write storage models. You see copy on write in ZFS, for instance. You see it in Postgres. There was a talk by OmniTI's database administrator yesterday on the details of how Postgres puts these new rows beside the ones that were written before, and puts a little expire entry in the old row to say, look, this isn't the most recent entry for this row anymore. It's been superseded. So copy on write's really nice, because you don't have this issue of writes that kind of might have succeeded, might not have, and you're not sure which state the data is in. Either the stuff was written, or you just don't care about that piece of your disk at all. And then a subset of that, of copy on write storage, is this log structured storage that I'm talking about, where copy on write, you're still kind of free to use any piece of the file that you want. But when we're talking about log structured storage, we really mean that every update that's applied to the file is always appended to the end of the file, right? So it's just a rolling log. There are file systems that use strictly log structured storage. There are not too many that are in regular use. That kind of access pattern is very useful for flash disks. So sometimes you see like the internal flash controllers implementing log structured writes, but the file system itself doesn't necessarily match up with that. But what you do see in some of these newer like NoSQL databases is strict log structured storage. One example would be the Bitcask storage engine in Riak, or the SS tables that Cassandra uses are kind of a variant of log structured storage, although they have this like in-memory component. But when everything gets flushed to disk, it gets flushed sequentially. And that has nice properties if you're talking about spinning Rust. You can minimize the number of head seeks you have to do bopping around to write things. You just always know you're writing to the end of the file, and writing sequentially is fast. And no surprise, since we're talking about couchdb, couchdb uses a log structured append-only B tree. And it's a fairly cool little piece of software, I think. So you have your B tree, right? And if you want to go ahead and update one of those leaf nodes down at the bottom of the tree, you can do so over there on the right. And you have to go ahead and rewrite the path to the root. So all those X's that you see there are the nodes that have been superseded by newer versions. So this has a couple of good features and a couple of downsides. The nice feature, besides the fact that you're only appending to the end of the file and never updating and overwriting storage that you've already written, is that this allows for a very nice, like almost trivial implementation of multi-version concurrency control in your database, right? So if you picture the case where you've got concurrent readers and writers, and you get a reader who picks up the old version of the B tree, picks up this old root header with the X on it, it can use that version of the database for as long as it wants, because that's going to be valid, right? We're never overwriting any of those underneath pointers, so it can continue to just execute its read operation or its stream over the database or whatever it's doing, knowing full well that all of this stuff is going to be valid for the lifetime of its transaction. So this really means that writers never block readers, and readers never block writers. Everybody just grabs, if they start a transaction, they grab the most recent header for the database, and they use that for the lifetime of their operation. So that's quite nice, and that's part of the reason why Couch does such a nice job of handling highly concurrent environments. Of course, it does mean that you need to compact these database files periodically. Robert yesterday talked about bloat in Postgres. For us, we just say you need to compact these databases. Because these nodes with an X on them are not useful anymore. Once the last client that was trying to read from this database is done reading, those are trash. We'd like to just deallocate them and be done with it and move on with our lives. And the way that we do that is by periodically slurping all of those entries into a new file that's written inside of kind of an optimally compact fashion, and then flipping the pointers over so that any new requests use the new database file, and then we can trash the old one. But compaction is just a fact of life for people who use couchdb, unless you have like a completely static data set, but nobody has that. And so the last thing that's really cool about this kind of storage engine is that from a durability perspective, the only thing that really matters is that you get that last piece, that last header, that root of the B tree, durably committed, right? You have to be really careful about writing that header, but everything else you just kind of write and say, okay, fine. If it crashes, all of that data is going to be invisible the next time I open up the database because it's not pointed to by the most recent header. So, that's OK. So you write all of your documents, you write all of the B tree nodes, you write the root of the B tree, and boom, then you commit your header. Once you've done that, you can report to the client that, yes, we've durably stored your update. You can pull the power plug. We don't care. It'll be fine. So that brings me to my next point, which is that it's a little harder to durably commit a single piece of data than you might think it is, or than I think it really ought to be. And part of the reason is that everybody lies. So what do I mean by that? If you take a picture of kind of what the system looks like here, And you've got your user space application with its user space buffer, and you decide that, hey, I want to write this piece of data. You execute your write system call. That keeps you up in the top piece of this slide, right? That takes your data out of user space and into the kernel's page cache, and it sits there. And it sits there for some amount of time determined by the kernel, depending on the number of dirty pages, depending on the time since the last flush. It's not on disk, right? It's just in a different piece of memory. And if you want to get it to disk, you can either just wait, or you have to issue an fsync call yourself, right? Fairly straightforward stuff. The trouble with the fsync, right, which is supposed to get your stuff from the page cache to the platter, doesn't really do that, right? It gets it out of the page cache and to the disk controller. And it's up to the disk controller to put this stuff actually on spinning Rust or on your SSDs or anything like that. Now, why is that a problem? Because we have caches all the way down. Ben Fried yesterday in his talk mentioned something about turtles all the way down, and I like that analogy. It goes back to a story about a scientist giving a lecture in the university hall about how the Earth revolved around the sun and the moon around the Earth and so on and so forth, all the astronomy. And after his talk, a little old lady comes up to him and says, no, it's really, the Earth is flat and, sitting on the back of a giant turtle. And the scientist smiles at her and he says, well, who's supporting the turtle? And she's like, oh, you're very clever, young man. It's turtles all the way down. I kind of feel that way with caches sometimes, right? To bust through all these caches and really force something down to disk can be a challenge. So you look at your laptop, and this is the sort of thing that you probably have. You've got a disk controller with no cache on it, and you've got the platter with some write-back cache. So it's caching the write requests that you ask it to do, some few megabytes of these, and periodically actually putting them on the disk. And it does this because it's a huge boost in write performance, and you would certainly notice it if you were to turn this write-back cache off. But the downsides are that in the event of a power failure, this thing doesn't have any sort of non-volatile aspect to it. It's just going to, it's memory. It's going to lose its contents. And so stuff wasn't really written even after you issued this fsync. So that sucks. And if you're running this on a server, you could be in a little bit of trouble. A better server would be something that has a write-through cache. So we don't want to get rid of the cache entirely. The cache is perfectly useful for reads. The more the better. But we do want to be careful to actually write stuff to disk when we can. So you could have a server that say, has a disk controller with a write-through cache, and the hard drives themselves have a write-through cache. That's fine. It's going to be quite slow. One thing that's a little better is if you can put some sort of non-volatile write-back cache on the disk controller. Maybe you have a battery backup module. Maybe you have some sort of non-volatile RAM. This is the mode that we have settled on for our physical hardware at Cloudant. I think it's a decent mix of being able to survive power failures while still offering halfway decent write performance. But again, this is all still physical hardware, right? A lot of people talk about the cloud. Cloud means virtualization. When you throw virtualization in there, things get more complex, right? You don't get this straight path from your virtualized page cache straight through to the disk controller. You go through, you have a virtual controller. It talks to the hypervisor. On the host system, there's another page cache. Now you're back to the disk controller. And so there's an extra level of indirection here. And it gets complicated because that hypervisor has to intercept all these system calls and implement them and such. And if you Google around for looking at old versions of Zen and that sort of stuff, there's some scary pieces there when it comes to ensuring that an fsync really gets implemented as a proper barrier all the way through. Right? This stuff can get bad. I think these days you can do it safely, but I asked the EC2 support team a little while ago about this and kind of went back with them for a while, and then they kind of went cold. So it can be scary stuff to do this in a virtual environment. We tend not to like to do that if we can avoid it. I should mention that all of this this sort of generalized diagram and stuff comes from a very nice talk on this topic by Ted Zuba. The link's down there at the bottom. So I pretty much stole his diagram of the I think he called it the trail of tears a bit takes on its way to the platter. But at the end of the day, you know, if you get the caches in the right setup with the right through cache on the hard disks themselves and some sort of safe write-back cache, you can still get decent performance and be able to write the stuff to disk that you actually care about, i.e. the database header in couchdb. So that's kind of the database portion, those two topics, log structured storage and how we actually commit this stuff. I'm happy to take any questions on that piece now because I'm going to kind of switch gears and start talking about distribution. So if not, yeah. How do you attempt to test this? I can't pull the plug in EC2, right? But you can do it, on your real servers, and it works. You can induce corruption if you don't do it, and not if you do. And in production, I have seen this happen on EC2, where some of our derived stuff was not f-synced. We would just write, and let the kernel flush it because we knew we could regenerate it on demand if we needed to. And after one bad power event, I remember finding between 1,600 and 1,700 of these files that were reporting some corruption, that they were just in an inconsistent state. Not one of them for the database files. We had a similar number of database files. Every single one of those was fine, and well over 1,000 of the derived ones were screwed up and had to be rebuilt. So I guess we tested it in production, and it works. Yeah. I didn't quite hear you. Yes. We don't break the header up into packets. It's just a single write for us. Oh, this is all strictly local. Yeah, we don't, yeah. We've never tried to actually commit the header non-locally on a different machine through the network or anything like that. I could see where that would be problematic. But what we do here is strictly, so, oh yeah, I should actually mention this. It's not enough to do one fsync, if you think about it, right? You need two. Because when you write this header, you have to know that everything it points to has been durably stored. It would be bad if you wrote the header and it pointed to stuff that was later actually not committed, right? That's really bad. That's data corruption. So you have to issue a write barrier, which you should be able to do with an fsync, to say, OK, make sure everything I've already asked to be written is on disk, right? Or rather, that everything that I've asked to be written will be written before anything I do after this barrier. Then I write the header. Then I issue another one to say, OK, flush that header. I really want it on disk, right? And if you don't do that last one, you run the risk of not actually having the header written and falling back to the last one. So that's not a risk so much of data corruption as it is just of losing the data that you've written since the last header. So yeah, it's a double fsync. The first question was, does the MVC implementation work well under what conditions? Yes, we do waste a lot of space. We have to compact down to compress things. And one of the downsides of using Couch is that the kind of working set space that you need can be really large if you have a high update rate. And we can see compactions that easily cut the file size in half, sometimes much more, depending on how long it's been since you last collected all the garbage. And so, yeah, it's certainly the case that that has bad effects. It starts reducing the efficiency of your page cache because you try to read some stuff into memory and it reads a little more, but the stuff it's reading is garbage. And so, yeah, I mean, it makes sense to compact regularly. On the service that we run, we have just a daemon that's compacting all the time, trying to pick the next one that's the best choice, the best bang for your buck to compact. And we have a little queuing system that kind of intercepts all of the I/O calls for the compactor to ensure that we can run it, even during peak times, and then it can just kind of use spare I/O capacity on the servers. It's absolutely something you need to do as part of your maintenance routine if you're running some form of couchdb. And you asked about garbage collection. Did you mean database compaction, getting rid of the garbage in the tree? Yeah, so the way we do that is not in place at all. We just actually have a separate file next to the one we're actively using. We grab, a certain header of the file, and we stream the contents of everything pointed to by that header to the new file. and then you kind of rinse and repeat until you've caught up to all updates that are happening while you're doing the compaction. Once that's done, you do an atomic switch over to the new file, and when every client is done with the old file, it gets released. We could be a lot smarter. I mean, you look at Postgres, they've spent how many years now optimizing vacuuming, optimizing auto-vacuuming, clustering, all that sort of stuff. We're just beginning to go down that route. At Cloudant, we've done some decent optimizations to reduce the amount of random I/O required to do the compaction, but there's still a lot, right? It's still fairly hefty. And I'm sure as the project matures to version 2 and version 3 and so on, there will be continued work in this area. Cool. OK, so on to distribution. Distributed concurrency. I mentioned at the beginning that couchdb has this incremental multi-master replication, right? Doing that is quite a bit different than doing like master-slave log replay stuff. That's a bit simpler of a sort of thing where you can just kind of ship your write-ahead log from your master database and replay those operations on any number of slaves. It gets tricky when you have to promote a new master to fail over to your backup or something like that, right? But fundamentally, like that procedure can be done without too many like core changes to the underlying data layer. In contrast, the incremental multi-master stuff that we do is pretty fundamentally different. You could absolutely be running 2 different couchdb servers, both of which update the same document to some different state simultaneously. And now we've got a situation where, one, we have to detect that that happened. Right? We have to detect that we have this mutual inconsistency, and we have to figure out how to deal with it. So there's a lot of literature out there on data structures that you can use for managing mutual inconsistency. Vector clocks are a common data structure that gets used. You'll find those in a product like Riak. Sometimes you can get away without this stuff. I think for at least some versions of Cassandra, if they detect some sort of mutual inconsistency, they just pick the one that has the later timestamp and throw the other one away. Right? That's an option if that works for your application. We went with the strategy that we're not going to presume a particular strategy, so we're going to have a data structure associated with every single document that is capable of detecting this mutual inconsistency and storing the versions for you. So, like I said, there's a bunch of these. And couchdb goes with one called hash histories. And so what those do is they deterministically generate an ID for every version of your document based on a cryptographic hash of the document's contents, right? And then you update, and they kind of roll that hash into the update and generate a tree of revisions of the document. And in the simplest case, when you're not doing any kind of multi-master fun, and you're just updating the document over and over and over again, your tree is just one linear path, right? And the only thing we really need to care about are the IDs of those and then kind of the leaf. We preserve a decent, some configurable length of that path for as long as we can. But the minute you do these mutually inconsistent updates, we branch the tree. And on replication, we synchronize those trees, and everybody agrees on the state of the revision tree and on the contents of the leaves of the tree. The leaves of the tree are the various versions of the document that you've got, the latest, sort of edit paths. If you think about it, this is kind of like what you get with a distributed version control system, right? You've got these commitishes, these hashes of your commits, and they form a tree. They've got branches. So there are a lot of parallels between what you might have in a Git repository and the internal data structure used to manage a document in this database. The differences between these kind of data structures, they can be important. I'm not going to spend a whole heck of a lot of time on them. The one thing that I should probably point out is that hash histories have this property, which can be an advantage or it can be a disadvantage depending on how your application works, which is that if you've got 2 different actors in your database and they apply the same update at the same time, the hash history is going to consider that to be the same update because you both had the same original state and you applied the same change. Maybe that's what you want, but if you've got a bunch of clients trying to update a counter, it's probably not what you want, right? If they're both trying to +1 and the database merges them together and says, okay, we incremented this by 1, that's bad, right? Fortunately, it's fairly simple to get around that sort of thing, possibly by just including the actor's name in the update. Now it's a conflict, and now you can resolve them by doing both increments together or something like that. There are other strategies, but it's one of those things that you have to be aware of if you're used to working with a system where the actors are implicitly included in the clocks like they are with version vectors, vector clocks, that sort of thing. A hash history can be used to reduce the number of conflicts, but only if you actually want to do that reduction. So it gets tricky, but the good thing is that all of this stuff, like I said, it's built deep into the core of the database. It's well tested. It's used all the time. And so if you come across a problem where you need, excuse me, where you need this kind of multi-master setup, it's good to have a database that was designed for it from the ground up. So I didn't mention it in the beginning, but couchdb and Big Couch are written almost exclusively in Erlang. There's a bit of C for some of the unpacking and packing of JSON and that sort of thing, but the logic is pretty much all in Erlang. Erlang was is a language that was developed internally at Ericsson originally for telecom operations. They open sourced it and support it. I think it's been generally a good choice for us. It has a few things that have made it possible for us to architect this scalable, fault-tolerant system more easily than we might have otherwise. Erlang depends on having lightweight processes, lots and lots of lightweight processes. We can run 1 million processes in the system without issue. And really, you can build systems that handle 1 million TCP connections if they're mostly idle without too much issue. It's mostly a shared nothing architecture. Every one of those lightweight processes gets its own heap. So there's really very little shared memory. If you do, there are data structures there that you can leverage shared memory for, but it's pretty explicit that you're doing so, and it's straightforward to architect an application where you don't have that. And that means that we can do a very nice job of kind of getting rid of lots of locks, which is good for the scalability of the system. These processes communicate with each other via message passing. So you have a message, you send it to a process. And all of the sort of internal server systems and everything in the programming language are based around sending messages to one another. And the interesting thing about that is that it scales to the distributed case. You can build a cluster of Erlang virtual machines on different servers, connect them up over TCP, and start sending messages to processes on remote nodes using the exact same syntax that you were using to send messages to lightweight processes on the local node. So you can build distributed systems rather quickly with this framework. So I alluded to it a second ago. One of the things that Erlang gives us is scalability across cores. Yes? Mm-hmm. Changes to a particular document or changes? OK, there is no time ordering. There's merely the version history. So these hashes form a tree. So I could have hashes 1, 2, 3, and 4 on one path, and hashes 1, 2, 3 prime, and 4 prime on another path. There's no time ordering per se, but we can tell that these two had a common ancestor at revision 2, right? Because the hashes match up at that point in the tree. And when we merge them, we can say, OK, 1 and 2 are shared, then they diverged at 3, and we need to keep both 4 and 4 prime around. But it's not a time-based thing. It's strictly these revision hashes are cryptographic hashes. So there's no sort of preference for last write or anything like that. Yeah. Yeah. That's right. So that was, if I understand your question correctly, that's the point of the hash history, is to recognize that there have been 2 divergent updates, right? And so the appropriate thing to do in that case is ask the system for all outstanding revisions of this particular document, right? So you get a list back instead of just the single object, and then it's up to you to figure out what the merge strategy is. Whether there's a sane way to merge both of the updates, whether you have to pick one and discard the other, that becomes up to the application developer. Yeah. So yeah, so back to scalability. The fact that there are very few locks, that it's mostly shared nothing, means that we can distribute these lightweight processes across multi-core systems rather efficiently. The programming language handles the details of the threading implementations and all that sort of stuff, which is very nice. And Ericsson works as hard to optimize their systems for multi-core and many-core machines. You know, you see them publishing benchmarks on Telera 64 chips and the like. But what we find these days is that we get basically linear scalability up to 8-core machines for our systems. 8. And we continue to see speed-ups up to 16-core machines. You know, you see like a 12x speed-up if you're using 16 cores versus a single one. So that has proven to be, you know, it's proven to be a good choice for us because we have these highly concurrent workloads that can leverage multi-core chips that are becoming, you know, increasingly cost-effective. And I'm sure there's going to be continuing work on that. It's mostly a game of find the lock, right? You'd be surprised how many things require locks. At least I was. Memory allocations are one area in which the programming language spends a tremendous amount of time. There's something like a dozen different allocators in the Erlang virtual machine for the different types of data structures and optimizing those for fast multi-threaded operations has been a long haul for them. So scalability across cores is one dimension. Scalability across servers is the other dimension, or an extension of that, I guess. And I put an asterisk there because I don't want to give you the notion that you can treat these remote processes as if they were local and just go on your merry way, right? There are very real differences in network latencies, in failure modes, in the fact that the process could just disappear off the face of the earth and you wouldn't know about it. I mean, it's a distributed system and the rules still apply. It's just that the programming model allows you to build servers using a similar syntax, using a similar set of constructs, and you know, we found that we were able to build systems to coordinate activity across our servers quickly and reliably with this framework because it had the notion of a distributed cluster of virtual machines built into it. It had a lot of kind of a lot of the details, a lot of the sort of networking details to kind of check for the liveness of a node, to allow you to subscribe to events when it detects a network partition, and you know, to kind of repair that stuff for you. There's a lot of work that goes into Erlang to support this use case of distributed clusters, and so we leverage that quite a bit when we're building Big Couch. All of the communications between the different individual CouchDB database servers in the cluster leverage distributed Erlang message passing to coordinate their activities when they need to be coordinated. And so that's kind of, so those were the topics for the distributed portion of this topic. A few details about Erlang and some details about hash histories and data structures. Any questions on those topics? No. So the last part I want to talk about is running the service, right? And so that means uptime. That means figuring out how to deploy code without scheduling maintenance windows. That means figuring out failover strategies and that sort of thing. So sticking with Erlang for a bit, one of the coolest features, in my opinion, for running the service that comes with the Erlang virtual machine is the ability to push code in real time without shutting down the virtual machine and have it upgrade versions of modules. So the virtual machine can support 2 versions of any particular code module simultaneously. And if you make a fully qualified function call to a module, right, to an exported function in a module, you'll always pick up the latest version. But if you're inside of a module and making local function calls, you'll continue to use the version of the module that, you know, was the one you started with, right? And so this means that you can develop strategies for the ways that you're going to push new versions of a particular module. If it's a functional module, generally speaking, you can just kind of loop back in and pick up the latest version of your code, and everything's happy. You know, pretty quickly, all the old versions are gone and are purged, and you can just keep going on this hot upgrade cycle, you know, ad infinitum. Sometimes, though, it's a database. There's state, and sometimes you want to change that state. You know, you need to upgrade the internal structure of a particular process in there, and that gets more complicated. Sometimes you need to do a synchronized upgrade of all of the processes running this particular version of a module, and that gets more complicated. And the Erlang framework has built up facilities over the years to allow for this sort of thing. So you can write, a function and tell the system, hey, when you're in the process of upgrading this, pushing this new version of the module, execute this function. I'll tell you how to transform my state to something that the new version can read, and we'll go on our merry way. And so this has been fantastic for us at Cloudant. We've done, we're not in a matter of continuous deployment. I'm not sure that's something we're ever really going to strive for as a database. Rollbacks are more complicated in stateful systems than they would be in, an application server. But we do deploy frequently, and we do have a system whereby, if we push code to master, we get the continuous integration server to build a release upgrade. It actually takes a look at what's out there right now and looks at the code modules that you've got now and analyzes the differences and executes, figures out what the upgrade instructions need to be. Okay, we've changed modules foobar and Baz. Baz looks like it needs a special system upgrade instruction, so we're going to write that in there. It generates this little tarball, pushes it up to Chef, and Chef ensures that these things get distributed out to the servers in our cluster. And then we get a human involved to actually trigger the upgrade and kind of watch the system to make sure we did something sane. Every once in a while, if we need to push hotfix, we throw a beam file out there. For a particular customer or something like that, we'll throw a beam file out there and just fire up a shell and load it in. But that's not something that I would necessarily recommend for long-term reliable operations. Pretty cool that you can do it, though. So, yeah. So the last topic that I wanted to talk about briefly is the domain name system, right? I don't think it gets enough credit sometimes. We've got these database clusters. Sometimes they span data centers. And there are load balancers in front of these things that need to stay up. If it's in one data center or you've got some sort of secure networking between them, there are tricks you can play with virtual IPs, Amazon's elastic IPs, that sort of thing, to give yourself an IP address that you can transfer between machines in the case of a hardware failure. And that's all well and good. But it's sort of the next level up, like, what if you really need to fail over to the other data center? And this is something that we've had to do. In that case, I think DNS is kind of the way to go. So that's good, right? We use it as a failover of last resort. But the other thing that we also do that kind of has turned out to be a fairly good thing for us is we use it for some configuration. When you think about it, these DNS providers that you find nowadays, I mean, they pretty much have 100% uptime, right? It never goes down. You've got this nested, cache-friendly, distributed NoSQL database in which you can put little pieces of configuration information. And there are RFCs out there describing how you should use DNS to do exactly that thing. So when we learned about that, we ended up pushing a few pieces of information that were fairly important for us, configurations of kind of cluster topologies and that sort of thing, pushing them into DNS and relying on the ability to kind of keep those things cached everywhere instead of having it in a service that we had written that wasn't particularly highly available. And we had to decide for ourselves, okay, do we harden this particular configuration API service, this internal API service that our customers never see, but which is important for us to keep up and running? Do we spend all of our time building an HA version of that, or do we go to DNS? And the DNS thing has been really positive. The only caveat that we've run into with this particular trick of service records and the like is that you can stuff too much information into them, right? You can get to a point where it exceeds the boundaries of UDP packets, and TCP DNS isn't always uniformly supported across infrastructure. So there's a limit to kind of the practicality for which you can use DNS to store configuration. Nevertheless, I think it turned out to be a fairly neat little hack that I would recommend for as appropriate. So yeah, I think that's about it. Finished a little. I think we have plenty of time for questions if you have any. Yeah, that's my context. Thanks.
So based on capabilities of your database, what models, do you have some example workloads or
Sure. So we have a couple of examples. One example that has proven effective, we have an advertising analytics company who has a number of campaigns, and those campaigns are treated as different databases. And they leverage kind of the multi-stage capabilities of our service in the MapReduce system to kind of crawl social graphs. They're a social advertising analytics play. And so they leverage the kind of the MapReduce, the internal MapReduce engine, which should not be confused with Hadoop, but can do a decent amount of sophisticated indexing that you wouldn't normally do on straight up SQL. So that was an interesting use case. We have a mobile phone app which uses a database for every one of their users, actually. So they stress the system in that particular dimension. They're going to have a million databases sooner or not. And they leverage replication quite heavily to share items between their users. So if they've got this collaborative nature of their application, and if you send an item to another user of that application, the system actually replicates the document from one database to another. So I think the mobile thing makes a good bit of sense because it's a web service that speaks JSON. So I mean, this is no surprise for any mobile application developer that's trying to incorporate remote data. So that seems like a fairly natural fit. In general, I wouldn't recommend it for systems that have a very high rate of updates to a particular document because there's an awful lot of garbage that we generate to handle sort of multi-version updates and that sort of thing. And if you really just need to keep a counter inside a document, you're going to be better off with Redis or something like that, right? Than you would be in a system that stores all of this version information. Yeah. So the way it works, and I think there's absolutely room for improvement here. But the current way that it works is that there is a call you can make to retrieve all the revisions of a document. You'll get back this array. All the leaves, yes, thank you. You'll get back all the leaf revisions, and you can then do an atomic update of all of those leaf revisions and say, I want to delete all of those leaf revisions and store this new one. Or I want to delete all but one of those leaf revisions and thus promote the one to the winner. And that operation that you do will then replicate to any other copies that you've been working with so that the conflict resolution itself is something that is shared amongst the replicas. I'd like to see a server-side display function, right? So that you could push, if you wanted for rendering purposes, right? If you wanted to push your conflict resolution logic, it'd be nice to be able to write a function that could deliver that for you, and maybe optionally do like some sort of asynchronous attempt to commit your decision as well. But focusing first on the rendering, just to kind of make sure that you can have that logic available on the server. But at the moment, it's something that you have to do in the background. That's right. That's right. Now, I mean, you could just tell them, maybe your application is fine with just picking one version. It depends, right? If it's a shopping cart, you probably want to, add both. But sorry? Yes. Oh, it's not shared storage. No. It's certainly each node in a big couch cluster is going to be a couchdb database in its own right with writing to local storage. And any of those servers is capable of calculating where a particular document ought to be stored. It does a consistent hashing thing, right? And routes that request to the appropriate storage server. And then if you're doing something where you have to actually sort of like get a view index of all of the data, right? You need to stream all of it or get some secondary index. That's a situation where you actually have to appeal to all of the shards and do a merge sort, and the system does that for you. Hmm? Yes. Right. So if a node, the question was, if a node goes down, how do you deal with what happens then? The normal way a big couch cluster works is that you set a replica level. Recommended replica level is 3. So every request to write a document actually maps to 3 shards hosting that document, and the document is written to all of those. And we'll acknowledge that as a success if we get 2 successful writes. On a read, a similar sort of thing happens. You issue read requests to all of the copies of the document, and you acknowledge a success when you get 2 that agree. Or if you find some inconsistencies, because, say, a node was down and you wrote to the document while the node was down, the system detects that inconsistency and issues a repair of that inconsistency while returning to you the winner of that inconsistency resolution. So if a node goes down, the system just keeps running, right? If 2 nodes go down, the system keeps running. If you're in a situation where those 2 nodes hosted 2 of the shards for a particular document, we'll report to you that, hey, we wrote the document, but not with the level of durability that you come to expect from us. It's in the system and is going to be replicated around as soon as those nodes come back up. But yeah, system stays available for writes the whole time. Any other questions? Okay, not. Thanks a lot.